this video, we are going to take a quick look at hydroelectric power and how it's implemented in the real world. Then we're going to look at tidal power and understand how it works through some diagrams or schematics. Next, we'll do the same thing for wind power. And lastly, we'll end with a derivation of the wind power equation, which applies for, what am I drawing? It applies to windmills, which turn. Right? And wind power is my favorite because windmills, the way I draw them, remind me of springtime because they look like flowers. Right? Here's my bee. Bzz. Okay, on to hydroelectric power applications. We're going to start with something unexpected, a coal power plant. In a coal power plant, we burn coal, and this is used to heat steam, which drives a turbine. But when we burn the coal, we get a lot of combustion gases that, in the end, just kind of exit through these stacks. Okay? And that represents heat loss. The heat that's being lost through the combustion gases is going into the environment. In there, it becomes degraded. We can't use it. But wouldn't it be nice if we had a way to not lose that heat, but capture it for useful work? Well, that's what we do in the case of coal plants that are located next to hydropower plants or hydroelectric plants. Hydroelectric power plants have two different basins of water. There's the reservoir on top, and then the river or the collector or some lower reservoir. Now, the way it works is we funnel the water in the reservoir down to the river. As it falls, it loses its potential energy, and that potential energy turns into kinetic energy, which spins a turbine, which we draw as a bow tie, right? And guess what? That turbine is connected to a generator. So it rotates when the water passes through, producing electricity in the generator. Right? So there's got to be a way to use the heat, right? Let's do this. Let's represent this by adding some tubes. This is not how it works, but it helps us understand. We connect the tubes to the stacks, which then sends the heat to the hydropower plant, and that heat is used to pump the water from the river back into the reservoir. So we use the heat from the coal plant to replenish our supply of reservoir water. And in that way, we allow ourselves to produce extra electricity. So we capture the otherwise lost heat energy from the coal plant. Now, hydropower is done in a couple of different ways when we connect our river to the plant. So let's say we're looking from above. Let me do this a little higher. Here's the ground, right, where there's houses or whatever we have on the side, and there's more houses over here. And this is a river in the middle with water. Yes, let me draw water waves. In order to produce a reservoir, which is at a higher elevation, one thing that we do is we put a dam across the entire width of the river, and we prevent water from flowing. So let me now look at this from the side. Here's the dam, which is nothing more than, well, it is more than this, but we can imagine it as just a really tall wall. So here's the water. But the water is flowing, let's say the water is flowing this way. So as the water flows this way, it hits the dam, and more of that water rises. The level rises. Right? And now what we have is a difference in height, which we can use to power a turbine by funneling the water down to the other side. So this powers our turbine, which is located inside the dam. Right? There's another way we can do this, though, right? Because this is problematic. Building a dam across a river is very expensive. It has environmental impacts, a lot of environmental impacts on the wildlife and water flow and water usage. It has lots of implications. So there's another way to do it without building a dam. Here's the other way. Let's move our houses. Oh, we have to tear down some houses. That's not good. No, the houses were never there in the first place. They were fake houses. Okay. Why am I still talking about the houses? Here we are. We take this river and we siphon away some of the water. Right? So now here are the houses. They were over here the whole time. I'm really concerned about these. And then we can use this this run of the river, this little run, as we call it, right? This run of the river, we can use that to basically do the same thing we saw before. Create a reservoir, fill a reservoir, and then allow, so here's the reservoir, and then allow it to flow into a lower collector. The run of the river empties into this reservoir, and then the water flows down, turning a turbine. And this is called a run of the river power station. By the way, all of these notes are written up in text form on page 4 of the handout from today, the 14th. That's run of the river. Good. So what have we done? We took some of that water from the river and we diverted it away on a little run, which is shown in the red. I have the word divert on page 3 of your notes, and the T is missing. Whoops. So correct that. The next thing we're going to look at is tidal power. And on page 4, the top right, there's a slide where I've left you some space to put a diagram. Now this is a complex diagram, so you may want to put it on another piece of paper besides those notes. And what we're going to put in our diagram is the Earth, the Moon, and the water. But careful, I'm going to erase and redraw the water in just a little bit. The moon is a mass. It's got mass. Water has mass. So I'm going to examine this water over here. And we could imagine different bits of water. We could imagine the water at the surface within this red box. We can imagine the mass of the water at the floor of the ocean. So the blue is the water making the ocean, and I'm pretending just for a second, for simplicity, that there's an ocean covering the full moon. Earth. This is the Earth. So, okay. You understand that ocean water doesn't cover the entire Earth. There's actually land, but we're just simplifying. Okay, good. Back to our two green strips. This is the water at the surface. Again, this is the water at the floor of the ocean. Newton's law of gravitation says that the gravitational force on my upper green strip is equal to big G, the gravitational constant, universal gravitational constant, times the moon's mass, times the mass of that surface water, the green strip on top, right, divided by the square of the distance, which is this. Oh, that's not so straight. Let me try again. So there is the r we would use in this calculation, right? But then I could also find the gravitational force on the mass at the floor, and if I wanted to do that, I would use this r, right? Slightly different r, which I'll call that r2.
Attention all students.
Okay, so I tried to pause for the announcement. It wasn't so successful. There's two different r's, r1, r2, right? And as it turns out, because we are going at this angle, right? Because we're going at this angle for r1 and at almost the same angle for r2, the distances r1 and r2 are virtually equal. Therefore, because the mass of water is the same, the gravitational force, let's do that in red, the gravitational force on the top water is pretty much equal to the gravitational force on the bottom water. And then, because they're equal, there's nothing weird happening, okay? Nothing weird. We can leave that water in that red box exactly as I originally drew it. So let me now take this all away, right? This water here is just as we've drawn it. What about over here, right? Well, in this box, we have some top water, some water at the surface. There's water at the floor of the ocean. And what are the distances? Ooh, look at that. The top water will feel a force. The force on the top water will be that. The force on the bottom water the top water is closer, so R1 is smaller. A smaller denominator means a bigger force, right? So the top water feels a slightly larger force than the water at the bottom, at the floor of the ocean. And that discrepancy, which did not exist here, and thus doesn't exist here, this discrepancy between the two forces, oh my, I can't make these videos after school. The discrepancy, or it has to be like 7 p.m. The discrepancy between the two forces produces a weird effect right here. Okay, let me take away the boxes. Here's the discrepancy. Here's the effect produced by the discrepancy. Whoops, I took away too much. The top water feels a bigger force than the bottom water, and that causes the top water to bulge out slightly compared to the bottom water, like this. So I'm going to erase and now draw in what you want as your final picture. We get this bulge, which I've exaggerated for purposes of the drawing. And guess what? There's a similar effect being produced at the other side, over here. Except for this, the water at the bottom is now closer to the moon. It's pulled more strongly. The water at the top is farther from the moon than the bottom water, causing the top water to feel a slightly noticeably smaller force than the bottom water. So let me draw that smaller force. Here's the force on the bottom water, and look at that, the force on the top water is just a little bit smaller, so we have a shorter arrow. And we can then infer that there is going to be a slight bulge over there as well, right? So I can erase this and show this bulge, as it's called. This is what the tides are. It's the bulging of the ocean due to the gravitational force uh, of the moon. And this we call high tide because the water is higher in its height. And this is low tide, right? And again, this would be high. And down here, we have low. The funny thing, though, is that the Earth rotates, right? It rotates like this way. So here's what we can do, which is so clever. We can put a we can put a little wall, right, like here. And as the Earth rotates this way, the wall rotates with it, okay? And as the wall moves over to here, if there's really a wall there, then we can trap some of the water that's coming. So there's like a water. We can imagine if we're moving to the right, then the water, it's as though the water is moving to the left, right? The water is moving that way, kind of, is the effect produced. Take a second to convince yourself that that's true. So we can, if the water is moving like that, as it comes forward, as we move our wall, and it slams into the water, some water gets caught, and it bulges up a little bit more, like that. And that allows us to put a tube connecting the two sides, and then we can flow water from the higher end to the lower end, producing electricity. Okay. The picture I want you to put in your notes, the first picture, is just the one with the two bulges at the high, representing high tide. The first bulge being here, the second here. So that's what goes into your notes, is that first picture with the two bulges. Don't worry about the wall quite yet. Now there's another slide on that same page 4 where it has high tide and low tide. I want to switch. It says high tide on top. I want to actually switch that and make this low tide that we're going to... We'll examine low tide first, and then we'll draw the picture for high tide after. So we have to correct the notes here. Right? Low tide. Here's the wall, and here's the ground. Water is at this kind of uniform lower level. Okay? We imagine that because of how the Earth is rotating, the tide, right, the high tide, which is over here, is coming forward toward us, right? So I flattened out the surface of the Earth, and this high tide is moving toward our wall. Don't draw that part unless you really want to. You can if you'd like. After some time has passed, we've reached high tide, but there's a wall blocking that high tide, so the high tide has approached the wall, but now there is the wall blocking the high tide from getting to the other side. High tide, low side. This is like a Dr. Seuss book. My favorite books of all. Okay, so we put a little channel between the two ends, the two sides. So we put a channel between the two sides. We flow water through. The water loses gravitational potential energy, which is converted to kinetic energy. The water's kinetic energy turns a turbine, which powers a generator. And this is how tidal power works. So we use the tides to generate a difference in between two sides of a wall, and from that difference in height, we drive a turbine as the higher water loses its gravitational potential energy, and that's our process.